Afternoon, everyone, or good morning or good evening, depending on where you are. Welcome to this parallel session on social complexity science applied to social systems. My name is Elisa Modei, and I will be chairing this session. We have 4 speakers. Each of them will have about 12 minutes to present their work, and then we will have about 3 minutes for questions. So please, if you have questions for the speakers, please type them in the chat while they speak, or at the end of the talk, you can raise your hand here on Zoom, and then I will give you the word. I'm not sure exactly how it works, if you can unmute yourself, otherwise I will unmute you as co-host of this Zoom session, so that should work fine. Okay, so then, maybe what I would recommend is that while the person is speaking, like only the person who is presenting maybe keeps the video on, and then we switch it. All the others we switch it off, just to ensure that the connection is as stable as possible. So without further ado, I pass the floor to June, who will tell us about the analysis of ethnicity networks using surname data. Over to you, June. Joomi, sorry, I see you're already on your second slide, but I don't hear any audio. I don't know if...
Really? Oh, sorry.
Yeah, I think when you share your screen, there is the option of sharing the audio as well, maybe.
I'm Joomi, and I will talk about analysis of the ethnicity network using surname data. Various techniques are used to study sociological changes, such as the movement of the population. The name data is one of them. The name data contains lots of information about the person. For example, the first name contains information such as gender, the trend of the ages, and culture and religion. Moreover, in the case of surname, it contains the roots of family, nationality, and ethnic information of the person. Name data is used in many studies because it becomes an information index to understand a person. So, and for example, it is used in areas such as biomedicine, demographics, marketing, and sociology, and so on. This name data allow for more predictive studies, which have recently been affected by improvements in computing power. Method for using vast amount of name data for prediction and classification, including machine learning, such as N-gram, Bayesian method, and SBM. And we use RNN in this study. A person's name is very interesting data. The data is built under the social, cultural, and linguistic influence of the person. Name data with these characteristics, we want to use the name to guess the family roots and connect it to the concept of ethnicity. And instead, we have massive name and nationality dataset. And by building a classifying model, we classify between nationality, ethnic origin with the surname. First of all, I will introduce a large scale of name data used in this study. We use all this 2016 data. And some of the samples from this data are shown as this table. This includes the data such as title and full name and place of birth, nationality, and so on. We used the surname and nationality data separately from this data in order to make a model of nationality classification according to the surname. In this study, recurrent neural network is used as a method of prediction using a vast amount of name data. Recurrent neural network, RNN, uses the concept of a neural network. For RNNs, the output from the front layer is used as the next input. This approach is appropriate to learn sequential data. An example of learning in this study is how RNNs do it. Use name and nationality data as a training data of RNNs. For example, we train the combination of characters like Smith as an English name. The names are all written in alphabet. And we also added LSTM layer to solve the vanishing gradient problem. The result of the test of classification model created are like this. We test the model with the test data and obtained computer metrics like this. This model is that it learns the distribution of names based on nationality or combinations of alphabetic characters. The test results show that different countries have different prediction accuracy. The brighter the color, the higher the accuracy. The distribution of regional prediction results according to test data inputs is like as follows. Iceland, for example, had a correct answer rate of over 90%, and Brazil had an answer rate of about 20%. The result of this prediction, we found that the characteristics of a country with high accuracy and low accuracy, compared to countries such as Iceland and Thailand, where the answer rate is high. Countries such as Brazil and Switzerland are very complicated countries in their ethnic composition. This is the classification accuracy of each country that our classifier has obtained from the test result. The average classification accuracy is 66%. We found something interesting in the result from the classifier. We guessed that the difference between a country with high predictive accuracy and a country with low predictive accuracy would be related to the complication of the actual ethnic composition. To confirm this, and the main ethnic groups of each country and their ratios were found from Wikipedia and World Population Review and World Fact Check. And compared to calculated information entropy in the classifier we built. So the result is this graph. And the higher the information entropy in the distribution obtained from the prediction result, the smaller proportion of the actual dominant ethnic composition. In other words, it can be seen that the countries with high information entropy are countries with high ethnic diversity. I explained how we use some data to build models and analyze them. There is something that needs to be resolved and demonstrated in order to apply this model more universally. It is to what extent this model can classify the concept of ethnicity. We used data of surnames and nationalities as training data, and RNA was trained to classify them based on the language structure. For research purposes, it is necessary to classify them that are the origin of the ethnicity, not nationality. So, to confirm this, we decided to examine and compare randomly chosen surnames from the Orbis dataset and compare with the classification result from human. For this purpose, we used mTurk. We picked data on several countries that could investigate it in mTurk, and people living in the area were asked if the name is derived from the area. Also, a filtering option was placed to determine the reliability of the response. For example, only responses were used with a name that could confirm the correct answer at a particular spot and made an accurate judgment of the name. Of the filtered responses, 90% of respondents the name true were given a name that originated in the region. We compared this data with the prediction of the model we built. Based on the values we set correctly, we found that the model got an average accuracy of 67%. The graph on the left shows the relationship between human judgment and the prediction of the model built. The x-axis is the name and the y-axis represents the ratio at which the statement was selected as the correct answer. Black is the response of mTurk, and the red line indicates the difference between low likelihood as the result value predicted by the model. What this graph shows is that the classified model also has difficulty in distinguishing the origin of ethnicity like a human has. In other words, the model classification of an ethnic group through surname is very similar to the degree to which a human distinguishes them. Next, we analyzed the spatial distribution of ethnic composition. The Orbis data used in this study contains information about nationalities registered by a person. There have been cases where such information have been disclosed. We gathered the data and analyzed the spatial distribution. In other words, we classified the regions that show similar ethnic composition. For this purpose, the similarity between the predicted distributions as a result of the classification was calculated with JSD. We used JSD as a weight to extract clusters of highly similar regions. We analyzed the African continent in this way, which is challenging to collect statistical data of ethnic composition. Names and nationalities of 48 African countries with sufficient training data were used to build a classifier for Africa. As a result, countries with similar ethnic composition ratios were able to be extracted. The mapping of 4 clusters to the map of Africa is as follows, and it can be seen that geographically close countries have similar ethnic composition. The result can be compared to the composition ratio according to languages and religions. We also analyzed the countries with high ethnic diversity on a city level basis. The name data used for this purpose were also always census data, with only a sufficient number of data used around the people whose city of birth was recorded. And Orbis data contains data on the business people, so we can interpret our analysis as a network of peoples in the economic field, not of the whole population. This is based on an analysis of ethnic composition of the three most data-rich France cities. Left side. For example, Paris or Lyon had the highest number of people identified as French, followed by Italian. Strasbourg, on the other hand, had the most significant percentage of German. We selected 14 cities with sufficient data for analysis and calculated the similarity of ethnic distribution with JSD, and we got 2 clusters. In the case of Switzerland, Zurich and Basel had similar forms of ethnic distribution. And in Switzerland, 3 clusters were obtained. It is divided mainly into south and north. It can be inferred that it is divided into French, Italian, and German and Austrian influences. And this is summary. We used large-scale surname data of business people and RNN to build surname origin of ethnicity classifier. We extract spatial distribution of ethnicity using an ethnic distribution that came from the classified wizard. And this is the further work. Thank you for listening.
Thank you very much, Joomi. We have time for one quick question. Is there any question from the audience? You can raise your hand or type it in the chat. Okay, I don't see any hand raised, so I will ask my own question. So, Joomi, I was curious. So, how did you deal with cases like, like where there has been a lot of migration? So, for example, at the beginning, you were showing Italy and Brazil, and my immediate reaction was, well, I guess like a lot of the family names in Brazil are actually Italian one, or some are Portuguese, some are Spanish. So
you mean the middle name or first name?
No, or even the family name. I mean, like places. Like, how would you distinguish between a name that like from a person that has Brazilian nationality versus Italian one? If, for example, that person actually has like Italian origins, or this kind of cases, like what's the label that you use? You only know the nationality, or do you?
Yes, yes. We make the classifier based on the nationality. So it's based on nationality. It had some difficulty to classify real origin of the ethnicity, but yeah.
Okay, thank you very much. Thanks again, Joomi. Our next speaker is, and yeah, sorry, like if people have more questions, feel free to type in the chats and the conversation can go on, of course, but in the interest of time, we're gonna move to the next speaker, who is Ajaykumar Manivannan, and is gonna tell us about informed design of future integrating developments using complexity science. Over to you.
Hello, everybody. with the focus on the spatial network analysis of an existing integrated development. Now, every year, more people move to urban areas in record scale, and cities have grown dense and vertical to accommodate this trend. This increasing density has encouraged cities like Singapore to design vertically integrated developments that rise to be the microcosm of cities, with hospitals, supermarkets, shopping complex, public transportation, restaurants and parks, all in a single or multiple blocks that are integrated closely. An integrated development can be defined as a mixed-use development with residential and commercial components that are seamlessly connected to transportation and public facilities. Integrated developments can serve as a solution to growing urban population. Besides as a solution to high density, they can also provide greater convenience and cost savings for the residents in the building. To demonstrate this, we took an existing integrated development in Singapore and studied the spatial network structure using commonly available tools in network science. In the rest of the slides, we will cover the description of the integrated development and its spatial network, the visualization of the spatial network, and a detailed analysis of the network properties, and some examples of how the study of spatial network properties can be applied to the design of integrated developments, and finally our planned experiment on collecting human tracking data. Kampong Admiralty is an integrated development located in Singapore, which will serve as our case study. Kampong meaning village in Malay language. It consists of 100 residential apartments for the elderly, 2-story medical center, special health facility for elderly and children, and commercial spaces like 900-seat food court, restaurants and retail outlets, and social spaces like playground, gardens, and community farms. It is also integrated with a train station and a bus stop. The nodes are selected based on the relevance to the study. There are 7 types of nodes: the residence, commercial, social space, the community facility, the food and beverage, health facility, and vertical streets. These pictures actually illustrate the spatial network of the integrated development for level 1 and level 6. The gray square indicates the vertical street nodes, and the green color indicates all the other types of nodes. The nodes that are actually of the same type with geographical proximity are actually combined as a single node. For example, many housing units that are placed adjacent to each other will be called as one single housing node. Edges are formed between immediately adjacent spaces. An exception to this is the within vertical street, like lift lobbies. Since we can actually potentially access any lift lobby directly from one level to another, they have an all-to-all connectivity when they share the same lift course. And this is a weighted network where the edge weight is the routing distance between the centroid of the nodes. 2 types of network is created. Network A, that actually considers the vertical streets like lift, stair, and escalator lobby as nodes, where hence all the vertical connections actually go through the vertical street lobbies. And network B, that doesn't consider vertical street as nodes, and edges are actually created across the floors between nodes that are immediately adjacent to the vertical street lobbies. This illustration for the network A with vertical streets considered as nodes. The picture on the left is colored by the floor level, and the picture is right is colored by the location types. Both pictures use the Ifan-Hu force-directed algorithm that uses attraction and repulsion of nodes to create the network layout. The presence of vertical streets actually provides a good connection between the floor levels, with each lift lobbies actually clearly seen as individual clusters. There are actually 5 main vertical streets, the 2 residential lift lobbies, 1 community lift lobby, 1 service, and 1 emergency lift lobby. In network B, where the vertical streets are not considered as nodes and simply as part of an edge, we see a network that reveals a high level of clustering, especially within homogeneous type of nodes that are actually present in different floor levels. So looking at the global network properties, there are actually 124 nodes in network A, and 55 nodes in network B. The number of edges are actually not very different, as we simply rewire the edges when excluding the vertical streets in network B. The difference in the global network properties of both these networks is seen through the average degree, the topological and weighted clustering coefficients, and graph density, which actually measures how close a network is to a complete network. So some global properties has not changed. For example, the average shortest path is around 80 meters for both the networks, and consequently the barycenter of the weighted network, the node through which the greatest number of shortest path pass through, is the same at pharmacy at level 1, that has a two-way path and connected to a core drop of area, and a community lift lobby that runs vertically through the spine of the componentality. The plots here shows the degree distribution of both the networks with node degree and the probability of its occurrence. For network A, the degree distribution is slightly broad, where the low degree nodes occur more frequently than the high degree nodes, but no real overall pattern is found. For network B, the degree distribution is mostly flat with a peak at node degree of 13. The peak distributions are actually very typical of many spatial networks, but not non-planar network like airport network has broad distribution like many complex networks. The graphs here shows the local clustering coefficient for each degree class. In network A, the clustering coefficient also increases gradually with the node degree, meaning that the hubs are actually highly clustered together. But in this case, the vertical streets makes up most of the high degree nodes. And in network B, the clustering coefficient peaks at the mid degree class nodes, but the clustering coefficient of a low degree node can be very close to a high degree node. This shows that the inclusion or removal of vertical streets as nodes have a significant impact on the network characterization. The graph here shows the box plot of weighted clustering coefficient for different location types. In network A, the vertical streets are actually highly clustered together, while the residence has the lowest clustering. And in network B, the community facilities has the highest clustering coefficient, followed by the residence. The graph shows the weighted betweenness centrality for each degree class. For both the networks, the betweenness centrality fluctuates throughout the whole spectrum of the degree class, meaning that a low degree node can be as central as a high degree node. That is, the number of connections for a space doesn't influence its ability to serve as a connecting path for a potential traffic. The graph here shows the box plot of weighted betweenness centrality for different location types. Removing vertical street doesn't actually change the shortest path calculations, so betweenness centrality behavior is the same for both the networks. We see that the social spaces have the highest betweenness centrality on median, followed by the commercial spaces, while the residents have the lowest betweenness centrality. This makes actually sense because it is likely the architects consider the privacy of the residents during design. They kept them away from being central to public traffic while encouraging it for social spaces. One potential application is quantifying the traffic congestion in vertical streets. The load centrality is a node centrality measure that calculates the fraction of all shortest path that pass through the node. And this table shows the floor level and the name of the lift stair lobby and the load centrality value itself. So the load centrality is actually equal for the residential lift stair lobby 1 and 2 and the community lift lobbies. But if you consider the number of lift cores, the residential lift lobbies has only 1/3 of that of the community lift lobby. So the residential lifts can potentially face more traffic than community lift lobby. We also analyze the accessibility of residents and non-residents to all the other nodes. The access from the residence to other locations in Kampung Admiralty is on average longer than for the non-residents who start at the entry points like car park or entrance area. But compared to the distance traveled by non-residents to reach there, residents can actually reach the key resources within 100 meters distance. So similarly, access to community form that is actually solely maintained by the residents is longer to reach from residents than from the entry points. But these observations are likely a compromise between accessibility and the privacy of residents by the architects. Like any network, spatial networks can actually be rewired or allocated a particular facility based on network optimization. The network properties that we have seen so far can be set as a goal to find optimal conditions for accessibility, reachability, and traffic conditions, while keeping some parameters constant, such as the total area of space or node degrees. The characterization of these networks are of course limited, where if you consider the node properties like area and sitting capacity and edge properties like travel speed, we can actually help improve this network analysis. We plan an experiment to take place next month, where 100 to 200 residents and non-residents will be recruited, where they install a custom mobile app that records barometer, that detects altitude change, and an accelerometer to understand body movements, and Bluetooth scanning that involves placement of Bluetooth beacons in the integrated development to help with localization. These data will actually allow us to have a spatial network with mobility traffic data as edge weight and use human co-presence behavior to derive some social metrics for each node. So to conclude, we have shown a framework to build and analyze the spatial network of integrated developments. We found that inclusion of removal of vertical streets can actually influence the network characterization significantly. So depending on the application, appropriate decision should be made. The privacy of residents is also an important consideration when designing integrated developments, as seen in their network properties. Like other spatial networks, we can also create network optimization models that can actually provide desired network properties like balanced traffic in vertical streets and accessibility that is tuned for each node. Thank you.
Thank you very much, Ajay.
Hi, thank you.
Hi. And do we have any question from the audience? We're a little bit behind schedule, but at least we can take one question. We have a very shy audience apparently today, so I'm gonna go ahead. I was curious, have you considered using as a modeling framework also multi-layer networks, since you have like this vertical, yeah, like I'm thinking maybe this could also be formalized that way. So I was curious if you considered that, what were the limitations?
No, we have not actually considered representing these networks as multi-lane networks, but it definitely sounds interesting to try it out in the future. Okay,
thank you very much. Thanks
again
for your talk. And we now move to our next speaker, Ravshanbek Khodzhimatov. I apologize today for not pronouncing well all the names I've pronounced so far. Is going to tell us about emergent social norms and their interaction with other means of behavioral control in complex adaptive agent societies. Over to you.
Hi. Really sorry. Could you hear the sound?
Yes,
okay.
For a second, yes, but then it froze.
Hi. In this presentation, I'm going to introduce our research on emergent social norms and their interaction with the other means of behavioral control in complex adaptive societies. I'm going to start by introducing the subject matter, describe our model, and show our findings. Consider an organization with 4 departments: production, finance, marketing, human resources. Organization operates as the heads of the departments make their decisions on the interrelated tasks. And as the managers communicate, the social norms are formed. And social norms are defined as the informal rules and standards of expected behavior in a society. Managers want not only to perform well, but also to abide by the social norms. Our research addresses the following questions. How do the social norms affect the performance in an organization? And how can the incentive schemes be used to influence the decision of managers in presence of social norms? To do that, we have to answer 2 questions. First, how are social norms formed? And the second, where do the social norms stand in the decision-making of the individuals? The literature gives us answers to both of the questions. So the first, social norms are formed endogenously from past behavior, and once they are formed, they proceed to influence the future behavior. And second, individuals consider the social norms as the goals per se, so they don't need any external reinforcement to pursue them. Let's introduce our model. We use NK framework to model the organization's task environment, and let's consider an organization to have 16 tasks allocated to 4 departments. Every single task is binary, so the decision is either 0 or 1. A decision on every single task yields a performance which is uniformly random according to the NK model formulation. To connect it to our example, let the first task of a production department would be to develop a feature A or not. The task 9 would be for marketing to market this feature A or not. And for the task 13 would be for HR to hire an expert in A or not. Go back to production department, X2 would be the decision whether to develop a competing product B or not. And finally, the X4, 8, 12, and 16 would be the tasks to allow flexible working hours or not. We can see that this decision is common to every single department. It is clearly that the tasks are interdependent because the performance phi 1, which is the performance of developing feature A, highly depends on whether the same department develops a competing feature or not, depends on whether other department markets it or not, or whether the HR hires an expert or not. Agents and managers perform these decisions at every single period during the lifespan of an organization. We omit the time indices for readability, but this decision happens every single period. This is the interaction matrix, a different way to model the interactions. We are going to focus on low, moderate, and high interdependence levels. So once the decisions are made and performances are computed, the performance of a department, let's say an HR department, is calculated as the mean of performances of the tasks allocated to that department. So for HR, it would be the mean of 13 to 16. And once the individual departmental performances are calculated, the organizational performance is calculated as the mean of the departmental performances, like here. So an HR manager wants to maximize income, which depends on the performance of HR department and the mean of performances of every single other department. And here we can see that it's a weighted sum. So the higher the alpha is, the more individualistic is the incentive scheme, and the higher the beta is, the more team-based the incentive scheme is. Social norms. Social norms are modeled when agents and managers, in our case, emulate the behavior of their peers. So we identify 2 types of tasks, private and social. Private tasks are unique to every single department and are not subject to emulation, and social tasks are common to every department and are subject to emulation. So here in our example, X9 would be the decision to market feature A or not, and this is a private task because only marketing does marketing. And X4 is the decision whether to allow flexible working hours or not, is a social task because every single department does the same decision. So our first expectation before we have any result is that the similar decisions not necessarily cause the similar performance, because the flexible working hours might work well for marketing, but not so good for production. Let's wait for our results, whether they will validate or disprove our claim. So we model the social norms compliance as follows. Let's say an HR manager made 4 decisions, and the last one is social, and it is equal to 0. The manager shares this decision with D other colleagues, so not necessarily with everybody, but with some subset of colleagues. And then every agent has a memory span. In our case, it is TM and is equal to 3 for simplicity. So in every memory span of an agent, library is formed. This is a library of shared decisions. And here we can calculate the compliance of the decision 0 on a social task with the social norms, which would be the frequency of 0 in this sharing library. So in our example, 0 appears once out of 3 times, so the compliance with social norms is 1/3. We can clearly see that this value can be as low as 0 and as high as 1. Once agents have the income and the social norms, how do they balance these 2 objectives? They use the concept called goal programming to balance these 2 objectives, which works as follows. Agent sets goals for income and sets goals for social norm compliance, and calculates the underachievement of those goals as the difference between the goal and the actual achieved income or social norms compliance. And if the goal is achieved, the value is 0. If the goal is not achieved, the value is positive. So agents want to minimize this sum of the underachievements. And if the goals are pretty low, the underachievement would always be 0, and vice versa. So this is a quick process overview. Modeler sets parameters and initializes the simulation. Agents share the information, perform the decision, which yields the performance, and we observe that performance. And they forget the social shared information that exceeds their memory span, and they go to the next period. So the performance looks usually like the following graph here, which is the x-axis represents the time period and y-axis represents the performance at that time period. We focus on organizational performance as our main variable of interest. And as we can see that this curve can have both different limits and different convergence speeds. So to combine these metrics, we use the concept of the area above the curve. But since the time is discrete, we use the cumulative distance to maximum, which is 1 in our case. And the smaller this d value is, the higher is the performance, and vice versa. So we run simulations with 90 different scenarios, and here are our results. We can see that we have 3 different scenarios for complexity, and for every single complexity, we have different levels of social norm goals. So it starts from 0 social norms to highly important social norms. And x-axis shows the incentive schemes. It goes from the individual incentive schemes to more team-based incentive schemes gradually. Our first result is that, as we can see, that regardless of every other parameter, the graphs get darker as the complexity increases, meaning the performance drops. This is an established finding. The more difficult the problem is, the smaller is the performance of an organization. Here, this is the answer to our first research question. How do the social norms affect the performance? And we can see as the agents start getting down on the y-axis, meaning considering social norms as more and more important, the graphs get darker and the performance drops. This is the first finding. And the second finding is that when the social norms exist in our model, which is the lower part of the graphs, we can see that the optimal incentive schemes is different according to the different complexity levels. So for low complexity levels and in presence of social norms, the optimal incentive schemes would be individualistic. And for moderate, it would be the moderate incentive scheme. And for highly complex environment, the best incentive schemes are more team-based incentive schemes. So in conclusion, what we found is that complying to social norms comes at a cost of a performance, which matches our expectations stated before. Second, the most important is that in presence of social norms, different incentive schemes are optimal for different complexity levels. Our further research is to analyze more the network structure, networks where the individuals share their social information, and to consider different incentive schemes to linear ones. Thank you very much for your attention. I'm going to wait for your questions if you have ones.
Thank you very much, Ravshan.
you.
Thank you. So is there any question from the audience? I realized, by the way, that if you can't, if you don't manage to raise your hand or unmute yourself, I don't know exactly how the settings are. You can also type in the chat that you have a question and I can unmute you. So we have a question from Chico Camargo saying that this is cool work and is asking if it's published anywhere.
Yeah, we submitted it to a conference. We're waiting for the results, publishable conference.
Okay, thanks. So yeah, like let's stay tuned for the published version then. Okay, if there's no further question, I think in the interest of time, we're gonna move to the next speaker. So thanks again, Ravshan. Our next speaker is Jonathan Donge, or Donges, I'm not sure, and he's going to tell us about social tipping processes for sustainability, an analytical framework. Over to you, Jonathan.
Yes, thank you. I'll try a live presentation. So I'll present work that we've been doing with different groups, but mainly driven by the Earthstock Network and the Earth League and the Dominoes project. And what is the motivation of this? Okay, let me start this properly. The rate of reduction of emissions that is needed to reach the Paris climate targets is huge. So if we compare the rate of reduction that is required in the future under really transformative climate mitigation scenarios, this goes down to 20% reduction per year, while in the past 70 years or so, we've seen mostly a growth of 1 to 3% per year. And only in times of major crisis, like the Second World War and the collapse of communism, the growth rate has slowed down actually, and we have seen negative changes in the emission rate per year. Now, how can we achieve these huge rates and go to these transformative pathways like the 1.5 degree pathway that can actually help us to meet the Paris climate targets? Empirical evidence for potential social tipping dynamics that could potentially trigger such large rates of change is abundant in history. There are societal transformations, revolutions, collapse of complex societies, and their resilience that have been studied in a large literature. And we've been asking in one expert elicitation that we did in this Earth League network with Ilona Otto, Roger Cremades, and Arvid Bovik and others, what are actually processes, social processes, what are social tipping elements that could initiate such socially and economically disruptive transformations that would lead the world to a complete decarbonization, or at least carbon neutrality by 2050, which would mean to really mitigate dangerous climate change. And we've identified a number of social systems like information feedbacks, financial markets, human settlements, energy system, norm and value system, and education that are relevant. But now, how can we actually analyze these systems in a systematic way? How can we analyze data in a systematic way, and how can we model these systems to understand how such transformations could be triggered? This is kind of what led us to the work that I will present now in the following. We've seen, to give you some more evidence, we've seen quite disruptive changes in behavior and attitudes towards climate change, even in the past year or so. The early 2019 saw the rise of the Fridays for Future movement in Europe, but also worldwide, that where you can see here, only in Germany, the percentage of German voters that thought climate change and the environment are an important problem rose from an average of 10% over the past 20 years up to 60% in just 2 years. This is a really disruptive change, and this even had an impact on the percentage of voters that would say that they would vote for the Green Party. This also went up from an average of 5 to 10% up to 30%. Of course, now with Corona, things have been damped down again a bit, but this is still quite a significant effect that you see here in the data. Now, the question is, of course, what is the mechanism behind that? But it is something that one can look at. A lot of work has been some high-level papers have been covering this topic recently. So this general question: are there these positive tipping dynamics that could actually mitigate climate change? And there's also generally an increasing interest in this topic of social ecological tipping dynamics in the literature. This is from a literature review that we did. Even over the past decades, you can see this particular rise starting in the 2000s here. Now, what is the commonalities of these processes? Social tipping dynamics are systems where small interventions can have large effects. That's quite generally the case. So this is the concept has deep roots in social sciences, going back to Schelling and Granovetter and their famous models. And the recent literature review confirms that. There's evidence for social tipping effects in data and models in history, as I said, in systems like public opinion, social norms, like in the talk that we've just seen, investment choices on financial markets, behavior, etc., etc. And there's even recent experimental evidence from behavioral experiments that shows something like a Pareto principle for social tipping, where it was shown that 25% of a minority or so of actors are sufficient to actually change the majority's attitude. So it turns out that a committed minority can often overrule the majority and really change the overall direction of the system. And this is consistent with what has been called social tipping before. Now, we realize that there are key differences between social tipping dynamics and the tipping dynamics that have been much more deeply studied, namely the ones in physical systems and ecological systems, where in physical and ecological systems, nonlinear dynamics, bifurcations, phase transitions have been studied a lot, particularly in this complex systems community. Of course, it has also been studied in social systems, but we realized that there are really these key qualitative differences, and there are 4 of them. The first one is agency. The second is network structure and social structure. The third is are the spatial temporal scales. The fourth is the complexity of the systems. And I will go through them. And this is these 4 characteristics are the ones that we built our analytical framework around. So agency is human capacity to exercise one's will to make decisions and consciously chart a path of action that shapes future events as well as the environment. And there, the notion of intentionality is important here. This is something that we can only attribute in a limited way to ecological systems, but certainly not to physical systems like ice sheets or the ocean circulation. Greta Thunberg here on the right might be one such actor where we could attribute agency to, that might have triggered a social movement like the Fridays for Future movement. The key differences now, okay, this is popping up. Network structures, social structure and networks are also very important. This is something where the element of networks is of course present in ecology as well, in ecological systems, in the biosphere. If you look at it from an Earth system perspective, but they are not as important, certainly in physical systems. So network structure and these effects for social tipping include the ability to consciously create and destroy links or nodes, where the links might be connections via infrastructures like the internet. They can be geographically confined, they don't have to be. And new nodes might be institutions, social norms, groups, or organizations, for example. And the tipping could occur on a given network, for example, through a spreading process or contagion process, as is shown here in panel A, or it could be through a change in network structure itself, like we see here through a polarization of a network. This is the US Congress divided into Democrats and Republicans and their commonly shared political goals, where you see this clear polarization, which has also been described as a form of social tipping or phase transition. Spatial and temporal scales are important. It has been shown in different reviews here by Lenton and also in our paper that these different systems that have been discussed as tipping systems live on really different scales, from days to millennia, and from spatial scales from local to global. But the climate tipping elements, for example, they tend to live on larger scales in time and space compared to the social tipping elements. And it also seems like the climate tipping elements seem to be more localized in this space, while the social tipping elements are more spread out, sometimes quite ephemeral. For example, political systems and technologies ranging quite a spread of scales. And this is also an important thing to look at when describing these processes, how to deal with these scales. Finally, this is of course here related to the topic of this conference very much. Social tipping processes occur in complex adaptive systems as opposed to the complex but non-adaptive physical climate system. The ecological systems are here again somewhat an intermediate case, and they can exhibit comparatively greater complexity in the drivers, the mechanisms, and the resulting pathways of social tipping processes. And greater complexity can mean a larger number of variables, for example, higher dimensionality, larger diversity and heterogeneity of processes that are involved. And then there's the diversity of actors and elements, different outcomes generated by local and global interactions. Development pathways of these systems are less predictable. And finally, it is often unclear what the final stable state of the system will look like. Predictions are often not feasible, or even whether the changes resulting from a tipping process will be normatively considered as positive or negative. And this is much more, in these 4 dimensions, we argue that the social tipping processes exhibit much more complexity than climatic or ecological processes. Now we come to a definition of what we, kind of a network-based definition of what we mean by a social tipping dynamics, a social tipping system. First, we consider a social system to be a network-like structure that consists of agents, social agents or subsystems, and other entities, could also be institutions, social norms, and so on, that is embedded within a social ecological structure, the environment. And this social system could also be a multi-layer, multiplex network, whatever you like, of course, but it is certainly possible to describe it by a graph or hypergraph type structure, or that's what we propose at least. And then this system is called a social tipping element if under certain critical conditions, a small change in the system or its environment can lead to a qualitative macroscopic change in the system, typically via network effects. And then in our paper, you see the archive link down here. There are also a number of examples, of course, given for these different for why this definition is useful, we think. And this can be then applied to data analyses and to modeling of different kinds. And I want to go a bit into, finally, to close off, into some modeling that we've done along those lines. So we are following, in the spirit of our definition, we are following a modeling approach based on the idea of adaptive co-evolutionary networks put forward by a number of people, but Thilo Groß and Dan Blasius, and also Sayama. They have put forward nice reviews on this. And the idea is that these are models where the state of network nodes or agents determines the topological evolution of network structure, which in terms determines the local dynamics of the nodes, which in turn can change again the topological evolution. So you have these feedback loops going on. And a lot of the models of different types of social tipping can be framed in this way. And one study that we recently published is this by Marc Wiedermann, a postdoc in our group. It's called the Network-Based Microfoundation of Granovetter's famous threshold model for social tipping. So what we basically do is that we connect Watt's famous 2002 model of cascading dynamics on networks and use this as a microfoundation. And it turns out that Granovetter's threshold model emerges somehow as a macroscopic approximation of the Watt's threshold dynamics model, and we can even extend it to improve the model to kind of be able to fit it more closely to real-world situations, where you actually have typically actors can be potentially active, they can be certainly active, or they can be in somehow an intermediate state. And this gives us quite a possibility to really link this to more realistic situations, for example, in the context of climate change awareness. And this will be certainly something to be presented in the future. Here we see some of the nice bifurcation diagrams and phase diagrams that emerge out of this. For example, you can see tipping points where increasing the share of certainly acting individuals, for example, individuals that are certainly engaging in a social movement because they are directly affected by climate change. This would be the certainly acting individuals here in panel B. And you see that if you increase this across a certain threshold, the system will tip to a state where much more individuals in the population are active. and vice versa. So there's also hysteresis in this system, and also a nice caste bifurcation if you look at two parameters. Now, to summarize, social tipping dynamics is a form of social change that could be key for triggering rapid decarbonization and sustainability transformations to tackle the climate change and other big problems that we currently face. Social tipping dynamics could be involved in relevant human-Earth system interactions and feedbacks, and hence should be studied for understanding the future dynamics of the Earth system in the Anthropocene. And then finally, first steps in collecting empirical evidence and modeling are done, but much work, of course, remains. And we're working on this in the Dominos project here, some links on the right-hand side, for example. And with that, I thank you very much for your attention.
Thank you very much, Jonathan. We have a question from the audience in the chat here. So Roger is saying, well, first, thanks for the nice talk, Jonathan. And then he would like to know, how do you differentiate the social tipping that crosses scales from local to regional and global phenomena?
I think this is a great point. These cross-scale dynamics can be, of course, very important. So then in many cases, or in some studies, it has been suggested that such social tipping or the transformation can either would emerge from local initiatives and then going up in the scales until a more global tipping is achieved. But it could also be that it goes from top down to the bottom, right? And it's actually something I think that at least we haven't studied this systematically with our approach, but it would be very interesting to do this with models, for example, to study this and to link it more to the empirical studies and to the social science work that has been done along these lines of cross-scale dynamics, as it's usually called. I mean, that's basically all I can say here, but certainly it's possible to classify different types of tipping also in that way, whether it goes from bottom up to top down or the other way around, for example.
Okay, thanks. One final question from Joel. Can you talk about how validation of such tipping point models can be done?
Yeah, good point. I mean, what we can do, for example, is that we can study certain cascading dynamics that are observed at least macroscopically, like in the Fridays for Future movement from the German survey data from the Politikbarometer that I've shown in the beginning, and we can see under which parameters our model produces a similar dynamics. And if we have microdata on actual network dynamics, we could get this potentially from social media data. We could also use this to parameterize really the micro adaptive network model. And we've done some work in this direction. So you can use machine learning to learn the underlying parameters of a certain network model based on such data, and so on and so forth. Or you can do experiments, behavioral experiments to do this. This is also a track we are following in our group.
Okay, thank you very much again, Jonathan, and thanks to all the speakers of this session. Now there is a coffee break, and then don't forget the plenary talk by Matthew Jackson at 3:05 GMT, and which will also be followed by the Complex System Society Awards ceremony and the talk by the awardee of the Senior Award, and then the roundtable on COVID-19 and complexity science. So yeah, have a great rest of the conference, everyone, and see you later.